Welcome to today's webinar, Log Analytics with Amazon Elasticsearch Service and Amazon Kinesis. Our presenters today are Alan McInnes and John Handler. Today with us, we also have an awesome team of Q&A moderators. We have Carl Meadows, Lex Crossett, Bruno Faria, Maggie Zong, as well as Darren Briskman. Thank you for joining us. They will be our webinar moderators who will be engaging with you and answering your questions throughout the presentation. Alan and John, welcome. The floor is now yours. You may unmute your microphone and begin.
Good morning, everybody. Thank you for joining today. My name is John Handler. I'm a solutions architect with Amazon Web Services, and I focus on Amazon Elasticsearch Service. Alan, why don't you introduce yourself?
Yeah, hi everybody. My name is Alan McInnes, and I'm also a solutions architect with AWS. I focus on Amazon Kinesis and streaming data in general.
Alan seems to be having just a touch of issue with his microphone. We'll get that straightened out. Alan also a solutions architect with Amazon Web Services. And we'll go ahead and get started. Alan will be talking in a little bit. So, you know, in motivation and preparation for the talk today, let's think a little bit about logs. When something's not working, the first thing you need to do is go look at the logs. In fact, logs are tremendously useful, not only for debugging, but also for figuring out exactly what's going on in your application, in your environment, etc. In fact, they're so tremendously useful that we've started building more and more logging infrastructure in order to enable the kind of debugging and monitoring that we want to do. The problem is, while I can look at this particular log, and if I happen to be in the right place, I'll see exactly the information I need. But if I have a terabyte of this information, it's very difficult for me to dig in with just tools like grep or Emacs or what have you to pick out the thing that I really need. This is kind of a tree's view of what's going on. In contrast, what I'd really like to have is to take that terabyte of logs, dump it into something, and make easy visualizations that will allow me to see an overview of the problems, a kind of forest level view, and dig in and figure out exactly what's going on. So we're going to talk today about, on the one hand, Elasticsearch and Kibana, and on the other hand, about Amazon Kinesis. Amazon Kinesis Firehose. So Kinesis Firehose is a streaming pipeline that allows me to get my data into Elasticsearch service, and now with transforms allows me even to transform the data on the way in. Elasticsearch service is an easy way to scale and manage Elasticsearch on the AWS cloud. With Elasticsearch service, we take care of the undifferentiated heavy lifting and allow you to run Elasticsearch and Kibana very simply from the AWS cloud. So let's talk about some of the features of Elasticsearch service. The first one is that, you know, again, we are doing the undifferentiated heavy lifting. When you use Elasticsearch service, you deploy a cluster into the AWS cloud via the command line, API, SDK, or console. Just a few clicks, you'll be able to set up a cluster, specifying your data and master nodes, and some of the additional AWS features that we provide. We also make it very simple to scale your cluster, so you're able to send, similarly, another API call that will change whatever configuration you're running. If you're running on, say, 4 data nodes of R4X large, and you want to run on 4 data nodes of C4X large, you make a single call. We transform the cluster in the background seamlessly, bring in new nodes, and make those nodes available behind an endpoint. So the solution is scalable. It makes it simple for you to try things out, see whether they work, change the underlying infrastructure and bring it more in line with what you need. We also have some features around high availability. So with Elasticsearch Service, we make it simple to deploy your Elasticsearch cluster into 2 different availability zones. We are open source compatible. So with Elasticsearch Service, we provide you an endpoint where you send your queries and your updates, and we do the security around that. But at the same time, you use the native Elasticsearch API to send your data into Elasticsearch Service. The security we provide is through AWS Identity and Access Management. When you send requests to your Elasticsearch Service endpoint, you create an IAM policy that specifies who has access to that endpoint and what requests they can send, and even down to the index level, what they can access. There are 2 strategies. You can do it by IP address. So you can specify requests originating from a particular IP address are able to access a particular index with HTTP post requests, for instance. The second strategy is to use an AWS principal. So either a user or a role. You can specify, again, access down to the HTTP method and index level. And with principal-based access control, you send AWS SigV4 signed requests. We authenticate those requests and then either allow or deny the access. Finally, we have a number of different integrations with other AWS services. So as we'll talk about, principally at the moment, Kinesis firehose, but additionally we have console-level integration with Amazon CloudWatch logs, with AWS IoT, CloudFormation, and of course Lambda is always a possibility for connecting with the service. So let's talk about a couple of examples of customers who are using Amazon Elasticsearch Service. The first one of these is Adobe Developer Platform. These guys have a major monitoring infrastructure that's looking at API calls to their system. It's an extra large use case with over 200,000 API calls per second, and they wanted to get that data into Elasticsearch Service. They use Kinesis and Spark to actually build that data into a little bit more rolled up form and then send it to Amazon Elasticsearch Service. During the kind of POC phase, they actually had a number of different configurations that they were able to try out very quickly through using our console and through changing the configuration of their cluster. That made it really easy for them to dial in the kind of scale that they needed. Second example is McGraw-Hill Education. McGraw-Hill Education provides online learning, and they have a wide catalog across many different locations and places, and they have tons, 100 million learning events a month. They wanted to ingest all of this data to look at online participation, both from monitoring a student perspective, as well as monitoring their teachers and the software itself, and figuring out whether it was effective and where they could make it better. So they ingest all of that, those learning events into Elasticsearch Service. They are able to look at a long time frame and use Elasticsearch's analytics capabilities to figure out what's happening with their teachers, with their students, and with their classes. They were very interested in the ability of the service to scale up. They're starting, they were starting at the beginning of the school year with a small amount of data, and as the year progressed, they needed to feel confident that they could build up and hold all of the data across the entire school year. So Amazon Elasticsearch Service's ability to scale gave them that confidence. So we're going to take a little bit of a dive through the AWS console for Amazon Elasticsearch Service to just touch on a couple of the points as we go through and fill in some details about Elasticsearch and about the service and how you use it. Again, as I said, when you use Amazon Elasticsearch Service, you create what we call a domain. A domain wraps not only the Elasticsearch cluster, but also provides additional software and other AWS services involved in bringing that cluster to you. So the cluster itself is launched into a service-managed VPC, and the nodes within the cluster are managed by the service as well. On those nodes, we provide Elasticsearch, of course, and then as well we provide Kibana. We front that cluster with elastic load balancing and publish the address for that ELB through Route 53. You make API calls directly to Elasticsearch API calls to that endpoint. These are REST API calls, along with whatever signing is required, or if it's IP-based, we use IAM to do authentication and access control and allow or deny that traffic. In addition, in the back end, we use CloudTrail to provide auditing information and CloudWatch to provide metrics around the functioning of the cluster. So this is a shot of the AWS console, and what we're looking at here is the domain creation wizard. And within this wizard, the first thing that you'll confront is a question of how many instances do you want? How many data instances? And this is a point where many people want guidance and help. Scaling Elasticsearch correctly can be a challenging task. So let's have a sort of look at some of the issues that go into figuring out how many instances you need. And we have to back up a little bit and talk about how Elasticsearch stores data and how it deploys that data to nodes, instances in the cluster. So a typical data pattern for a log analytics use case is to create an index for a particular time period. Normally, we would create an index per 1 day of logs. And as we flow data in, we'd send each of those log lines into the index that corresponds to the day that it was generated. So in this example, we have an index per day looking at a 7-day retention time. And again, that's very typical to keep data in there for a week, maybe 2 weeks. In some cases, it can go much longer, but for log analytics, we usually see that people want to know what's going on kind of right now, not necessarily a month ago. Each of those indexes then is composed of a set of shards. You set the sharding through the Elasticsearch API when you create that index. The default value is 5 shards, 5 primary shards. We recommend that you have no more than about 50 gigabytes per shard, and you can have target about 30 gigabytes when you're creating the index and creating the set of shards. That gives you that 30 gigabytes, gives you a little bit of room to grow. For example, if I have about 300 gigabytes of data, I would create 10 shards. Now each shard contains the documents, a set of the documents that are part of that index. Documents are routed to shards based on a random hash of their ID, and that randomization actually helps quite a bit in keeping queries performing well. The documents have fields within them. Looking back at or thinking about the original logs, which were Apache web logs, we'd see fields like the host, the auth and ident, a timestamp, size, a URL, etc. Those fields comprise the documents, and they're what we use to search and visualize. So that is the logical breakdown of how data is organized into indices. Now on the flip side, Elasticsearch is responsible for deploying those indices onto a cluster of instances. So in this example I'm showing, I have 2 indexes here. Each index has 3 shards, and those shards need to be put onto instances. But you'll see I also have listed a replica for those shards. Within Elasticsearch, again, through the Elasticsearch API, you can create a replica for your shards. You can actually create any number of replicas for your shards. So we always recommend that you create one replica. That one replica provides redundancy, as we'll see. Because if we look at how the green index is deployed onto the nodes in the cluster, you can see that the red outlined primary is going on to instance 1, and the not red outlined replica is going on to instance 2. So Elasticsearch ensures that, provided that you have enough nodes, your primary and your replica will always live on a different node. That way, if a node is lost for any reason, you retain that data in the cluster, and if you bring a new node in, it re-replicates it so that, again, you have 2 copies of it. And the emphasis here is that the storage and the index structures that we're creating all live on these instances. So at a first level of description, I appear to be missing a slide here, so I'll just talk through it. To a first level of description, then, nope, I'm not missing a slide, sorry. So when we think about that storage, we have to keep in mind how much storage is going on each instance. Now within the service, you have 2 options for setting your storage. The first one is to use the ephemeral storage on the instance itself, and the second is to use EBS. If you choose EBS, we have various limits on the volume sizes tied to the instance type that you're deploying, but up to 1.5 terabytes of EBS can go on a particular instance. If you choose the ephemeral storage, again, depends on the instance. Our largest disk for an instance type is 1.6 terabytes for the i2 2x large. So in either case, you get roughly 1.5 terabytes of storage per instance. And we do recommend that you use EBS in most cases. Yes, ephemeral storage will give you a boost of performance, but we see it clocking in around 10%. So EBS is a fine choice and is usually a lower cost choice for larger storage sizes. So we have to go back to our console and answer our original question, which is how many instances? And as we've described it, Elasticsearch is basically using the storage on that instance to store the indexes. So to a first approximation, and leaving aside performance for a second, the number of instances that you need to start is tied to the storage. So you can start by looking at how big is that index. Now, generally speaking, the index is a structure that's created out of the original source documents according to the mapping that you set. In most cases, we see about a 1 to 1.1 correlation between the data size and the index size. Closing your eyes, squinting, and looking kind of over your thumb, you can basically think of the index size as roughly the same as the size of the documents that you have. So if you're using a replica, and you should, you need to double that because both the primary and the replica will be stored. And then you can size based on those requirements. And using 1.5 terabytes of EBS, or thinking about 1.6 terabytes of i2 2x large storage, you can simply divide. So for example, if I have a 2 terabyte corpus, right, that means I need to store that 2 terabytes roughly of index. If I add a replica, that will be 4 terabytes of storage that I need. And if I use the 1.5 terabytes of EBS, I would get 6 terabytes total of storage. So 4 instances should be about right. In fact, it's a little bit too big, but there's a couple of other reasons to use 4 instead of 3. 3 would be 4.5 terabytes would be just closer. But when we get to discussing our high availability solution, we'll see 4 is a better choice than 3. So our next choice is the instance type. And within Elasticsearch Service, we support a number of different instance types. The T2s, we do support the smalls and the mediums. T2s are great for dev and test. T2 smalls are available for the AWS free tier, so you can use those to try it out. And it's a good entry point. But generally speaking, we don't recommend those for any kind of production workloads. We also support the M class instances, M3s and M4s. They are a generally well-balanced machine that we see as being appropriate where you have equal read and write volumes. Difference between the M3s and M4s, the M4s have a later generation processor and are EBS only. So M3 mediums can still kind of be appropriate as a good entry point as well, where you get a somewhat lower cost machine and with ephemeral disk. For the R-class instances, these instances have more RAM, and so we see them as being appropriate for cases where you're doing a lot of aggregations or a lot of analytics, as we'll see, as well for any kind of heavier queries or queries that touch a lot of data in the index. Those would be good instances. The C-class is actually, with the emphasis on processors, is a good choice for high concurrency workloads, things like heavy read traffic. Generally, the C-class is good to use for that. And the I2s are, again, our storage, ephemeral storage kind of workhorses. So we see those appropriate for the larger use cases where disk I/O is really key. And those will be high volume write workloads, typically in a log analytics case. So one of the service features that we provide is called, actually it's an Elasticsearch feature, the ability to specify particular nodes which are master nodes only. And as the service, we provide a simple checkbox that allows you to set up your dedicated master nodes. So what is a dedicated master? Well, all clusters, all Elasticsearch clusters have a master node. The master node is responsible for orchestrating between all the other nodes. In particular, it knows where all of the shards are located, and it is responsible for sending around mapping information to all of the different nodes in the cluster. Additionally, the other nodes in the cluster hit that node to pull out locations of the other shards, etc., so that they can coordinate the query traffic and the write traffic. So every cluster has a master, and that master is elected from a quorum of the eligible nodes. Now the problem is, if my master node is also doing a bunch of reads and writes, then it can become unavailable due to the load on it from those reads and writes. If my master node is unavailable, my cluster can dissolve. So that's kind of a bad thing. So what Elasticsearch allows you to do is to specify nodes that do only the master function. These nodes don't actually hold any data, don't compute query responses, and don't do writes. So you can specify a number of nodes that are doing just that and then put the data functions onto other nodes. Again, within the service, we make this easy. We let you just click that checkbox and then choose the instance type and instance count for the master nodes. We do recommend 3 master nodes. And the reason is that, again, the one cluster master is elected from a quorum of eligible nodes. You want to pick an odd number because that way, if you have a network split, you can only have 1/2 of the cluster that thinks that it can create a master and become its own cluster. So we have some criteria here for selecting master nodes. These are the instance types that we have tested out and have validated that we can use these instance types as master nodes and dependent on the number of nodes, data nodes that are in the cluster. So if you have fewer than 10 data nodes, the M3 medium or the C4 large, the smaller instances are fine. If you're between 11 and 20, then the M4, R4, M3, or R3 are fine choices. And then if you're above 20, and currently our service limit is 20, but you can file a limit raise request if you like to get up to 40 nodes. So for larger clusters, again, we want to look at the X-large class of instances, and those are good choices for master nodes in those cases. So another feature that we provide is a feature that gives you a higher availability, and we call it zone awareness. So looking at your cluster, your instances, if you don't select this, will be all in a single availability zone. Selecting zone awareness splits the nodes in the cluster into 2 different availability zones and makes sure that the primary and replica shards for your indexes go into different zones. That way you have 100% coverage in terms of the data in 2 different availability zones. So let's just talk about a couple of use cases and ways to get data in. Many of our customers are already using Logstash to get data into Elasticsearch, open source Elasticsearch. So for smaller use cases, we think this is still a fairly good pattern. You can use Logstash and connect to an Amazon Elasticsearch service domain. We provide a Logstash output that does AWS SigV4 signing, so it makes it easier to specify a user-based policy, send your data out with Logstash directly off the application nodes. And this is good out to a couple of 100 gigs of data, perhaps with M3 mediums and 100 gigabyte EBS data nodes. And we do always recommend master nodes for production settings. For larger use cases, we see a lot of customers that are sending their data to us via some intermediary. Sometimes it's DynamoDB, sometimes it's S3, sometimes CloudWatch. All of those, in one way or another, use Lambda to send data into Elasticsearch service. And again, this is up for larger use cases, can go up to a few terabytes of data, maybe 5. We look at the R3 or R4 class for the data nodes, and again, master nodes. When we get to the XL end of things, then we see a real need for the support of some streaming or buffering solution. And there are a lot of different choices here, but we're gonna focus in on Amazon Kinesis Firehose, and that's the one we'll take a look at. These are, for the XL use cases, we're talking the hundreds of thousands of log lines per second. We're talking sending that data to Elasticsearch through a buffered solution. So I'll just recap this section by giving a couple of best practices. You can start figuring out the number of instances that you'll need by looking at the storage you need total and dividing by the storage you need on each node. You can use GP2 EBS volumes, but we also see that the magnetic volumes are not really as good, so we do recommend the GP2 volumes. Use dedicated masters for production deployments. Turn on zone awareness, and there's an advanced setting that we haven't covered, indices field data cache size. I won't cover that now, but that's in the console, and you should set that thing to 40%. Okay, I'm going to turn it over to Alan now, and he'll guide you through a little bit of info on Kinesis and Firehose.
All right, great. Thanks, John. So as John mentioned, one of the more popular ways that many customers today ingest data into AWS for many reasons, one of which is to write it into Elasticsearch, is to leverage Amazon Kinesis. Now, Amazon Kinesis comprises of three different services, primarily Amazon Kinesis Streams, Amazon Kinesis Firehose, and Kinesis Analytics. We're going to talk briefly about each of them, and then we'll spend a bit more time on Kinesis Firehose as it has direct integration with the Amazon Elasticsearch service. So Amazon Kinesis Streams, the way to think about streams is it sits as a buffer as the ingestion service for any type of data. So now looking at this particular slide, you can see it shows clickstream data coming from a client of some kind, sits in a stream, and then you write your own custom consumer code to process the data out of that stream with your own custom processing. So the stream acts as a buffer for your data upon which you can act to take custom actions. Streams data by default will reside in a Kinesis stream for 24 hours, but you can adjust that to have the data be durably stored for up to 7 days. So it's easy to administer, a couple of clicks in the console or a basic command line or API call to create your stream, and you build your own custom applications on the back end. And it's low cost. You pay per shard. So we're not going to get into too many details around the sharding mechanism and the scalability component of Kinesis streams, but it's on a per shard basis. The next service that we're going to discuss is Kinesis Firehose. We're going to get into more detail with Firehose, but Firehose itself has integration with 3 different services on the back end for destinations. So with Kinesis Streams, where you're building your own consumer, Kinesis Firehose has a managed consumer already created that you just have to configure. So one of the things we noticed a couple of years ago when Kinesis Streams first launched was that many customers were doing the very same thing. They were writing data to their stream, writing a custom consumer in some language of their choice, and writing the data into S3. So many customers were doing very similar things with very little distinction between them. So that was sort of the genesis for Kinesis Firehose. We decided, well, if so many customers are doing this, let's build a service that makes it very simple for the customer, because they're all wanting to do a very similar, take a very similar action on the streaming data. And so that's what Firehose became. And so with Firehose, again, there's no administration of the entire service. You just set it up, you configure your destination, and today we're going to talk more about using Amazon Elasticsearch service as your destination. But alternately, you can write streaming data to S3 to be durably stored, or you can write your streaming data as well into Redshift, which is our data warehouse service. And Kinesis Firehose automatically scales as well. So as your ingestion rate grows, Kinesis Firehose will automatically scale to accept your growing rate of ingestion. The third service is Amazon Kinesis Analytics. We're not going to get into a lot of detail on that today, but I did want to bring it up because it's a relatively new service, and many customers who are using Firehose or Streams are also using Kinesis Analytics. So with Kinesis Firehose or Kinesis Streams, you're streaming data as it's ingested. Your consumer or Amazon Firehose will write your data to a persistent backend. However, if you wanted to do real-time analysis on that data as it streams through either Kinesis Streams or Kinesis Firehose, you can use Kinesis Analytics and do real-time aggregations on that data using standard SQL language. So it's very basic, a very simple service to set up and get some real-time insights into your data before the data even gets persisted in a backend. So if we take a look at Amazon Kinesis and we look at Firehose versus Streams, there's really kind of a distinction between why should I use one versus the other. The main reason that many customers choose Streams is they have custom processing on the data that's being ingested. So they want to write their own custom processing process on the back end to pull the data out of the stream, do their own data manipulation, do their own aggregations, and write the data to a custom source that's part of their infrastructure. Where Kinesis Firehose has a managed capability to do that. So where you get the simplicity in Firehose with a managed consumer writing to one of 3 destinations, Streams, you have to write your own custom processing logic to take the data off the stream. But if at the end of the day you're looking to take streaming data and write it into Elasticsearch so that you can use tools like Kibana to do some analysis on it, then Firehose is a perfect fit. So let's take a little bit of a deeper look into Firehose. So Firehose, the delivery stream is the underlying AWS resource. So data is buffered in a stream. It's not, the Kinesis stream is not made available to you as the customer using Kinesis Firehose. However, there is a stream that is part of the Firehose service that is buffering the data. You choose one of 3 different services, either Elasticsearch, like I mentioned, Redshift, or S3. And you also define a few properties for how long Firehose should buffer that data before it writes it to the destination. So with Elasticsearch, the amount of data that gets written to the Elasticsearch service in a single bulk update depends on one of two different, we call them buffering hints, that you create with Kinesis Firehose. So you either set a buffer size, which can be anything between 1 meg or 100 megs of data. So Firehose will buffer that amount of data, whatever you've configured, or a buffering interval. So some amount between 60 seconds and 900 seconds, which is 15 minutes. So you have to set both of those values. Whichever threshold is reached first triggers the flush of the buffer, and that's the data that gets written into the Elasticsearch service. Amazon Kinesis Firehose also automatically handles the data delivery failure. So for example, if for some reason the Elasticsearch service is unavailable or there's a networking issue of some kind, Amazon Kinesis Firehose will automatically retry to write the records to Elasticsearch, and it'll retry at a duration that you specify. So the duration, retry duration, is configurable as a part of the Firehose configuration settings. It'll retry for that duration. After that duration has expired, if it still wasn't successful to write the data to Elasticsearch, Firehose will write the data to S3. So you'll always have the raw data stored in the event that it couldn't be updated into the Elasticsearch service. A recent feature that was added to Kinesis Firehose, which is quite important when we're talking about ingesting data and writing to Elasticsearch, is the ability to transform the data in flight before it lands in the destination. So imagine that the source of your data isn't formatted in JSON. It is, perhaps it's CSV or some kind of unstructured data that you can tweak and create a JSON document before you write it to Elasticsearch for indexing. Well, with the Kinesis Firehose data transformation feature, you can create a Lambda function that will be called by Firehose to transform your data to the format that you've specified. It'll do this, it'll buffer up to 3 megs of data, Firehose will, pass those 3 megs to your Lambda function. In your Lambda function, you transform the data to be properly formatted for ingestion into Elasticsearch, and then the Lambda function will return that set of records back to Firehose for persistence. So if we look at this diagram at the bottom, we can see there's an array of records being passed from top to bottom, the bottom being the Lambda function. You can see there's a record ID, and then we pass in basically the raw source data, the encoded data. In our Lambda function, we transform that data, and then we return it back with the same record ID. That record ID is assigned by Firehose. So when Firehose passes a Lambda function 2 records, as it shows in this case, as long as the record IDs match on the return data set, my data attribute of the JSON record is going to be the data that you want to persist into Elasticsearch, and then you give us a result value of OK or dropped, or there's also a third, which is an error. So what happens here is when Firehose gets these back, so in this particular example, we see that 2 records were passed to my Lambda function. The resulting data set has also 2 records with the same record IDs. The result of one is OK, and the result of the other is dropped. And so what Firehose will do is it will persist the one that is OK, and it will my computer just crashed. I don't know if my audio is working through the screen, through the microphone, but my computer just died.
Okay, Alan, I can hear you through the microphone. Alan is having some technical difficulties right now. We'll see if we can get his audio back. Or if not, perhaps I can simply pick it up. So as Alan was describing, you're able to invoke a Lambda function inline with your Kinesis firehose stream. So what we're visualizing here, we have a data source which is generating records. This could be your application. It could be log files for the instances that you're running your application on. It could be any number of different data sources. Those data sources put records into the Kinesis firehose using that simple interface. Firehose will invoke your Lambda function with batches of those records. Your Lambda function can do any kind of processing you want. We see, again, changing from CSV format to JSON, or changing from Apache weblogs to JSON that Elasticsearch can accept. Those are very common. Some other things that you might do in there, though, involve decorating the records themselves. So in many cases, you might want to call out to a separate database to tag a particular log line with some information. You might do some kind of GeoIP lookup, and in other ways add data to those records that will enrich them and make them easier to use and search against. So the Lambda function returns those to the Kinesis firehose stream, and then that delivers the records to Elasticsearch service, again with the buffering and the retries that we talked about. You can also, at the same time, send failed records to an S3 bucket. So either for the Lambda invocations when they fail, or for delivery failures where Firehose is unable to reach the Elasticsearch service for any reason, you're able to direct all of those failed records into an S3 bucket to come back later and pick them up again and send them off. And at the same time, you can deliver all of the records that you're sending through to an S3 bucket. This is a really great way to get your log files into S3, which can serve as a backing store for later recovery or use of those records, for further exploration. So summing up a little bit, Kinesis Firehose provides you with serverless scale. You don't have to think about sort of the scale itself. There are some limits on the Firehose stream, but you can, again, file a limit request and get that raised as high as you need it. Additionally, it's a robust delivery system that provides not only retries, but error handling and delivering your records to S3. So it provides a lot of robustness in the ingest pipeline itself, totally serverless, easy to set up, and easy to manage. So a couple of best practices that we want to cover here. The buffering within Firehose is set based on either a buffer limit in terms of megabytes. So you can set your buffer size to be 5 and up megabytes, or you can set it based on time. So you can say every 60 seconds Firehose should flush or higher. So the smaller buffer sizes, again, would provide you a quicker delivery, of course, and potentially would cause Firehose to send more records. So you want to be careful of how often Firehose is flushing. As a broad point, looking at the capacity of the Elasticsearch service cluster to handle write traffic, you want to be careful to limit the number of flushes to be something like half of the CPUs that you have on the instances in the cluster. So you want to use smaller buffer sizes, and you have to balance that against how often is it flushing. If I'm sending 100,000 log lines per second, and I'm sending, say, 5 megabytes or 10 megabytes a second, then I'm going to trigger a ton of flushing out of Firehose. I have to make sure that my Elasticsearch service domain is scaled to handle that. Second thing is Firehose provides index rotation, and this will change over your index automatically at a hourly, daily, weekly, or monthly border. And really, as I said up front, the daily index is the most common pattern. When you start to get up in the tens or hundreds of thousands of log lines per second, though, it's appropriate to use the hourly rotation. And if you're really only sending thousands or tens of thousands of log lines per day, then you can expand that out to week or month. Generally, you want to kind of make sure the data gets partitioned in such a way that it's easy to manage and easy to, that the queries will run well. The default stream limits are there. Again, you can actually get those raised. The last topic we want to cover, and I'm going to cover it really quickly, I want to talk a little bit about the analytics that you can do with Kibana. And the analytics are based on a feature called aggregations. Aggregations look at a collection of documents, typically those documents that match some query, and then create buckets out of the values in the fields there. So within those buckets, it's that Elasticsearch then computes metrics across those buckets. The simplest metric is count. So in this example, we're looking at a time bucket. We've bucketed into particular time slices for, say, our Apache weblogs. We look at it, those buckets are perhaps 1-minute buckets. And then we count how many items are in that bucket. This gives us a simple graph that shows us the amount of log lines that are coming in. Now, as I said, typically we would apply some kind of query or filter that would limit or allow us to dig into a particular data set. So in this case, we're looking at a query that is host 199.72.81.55, and we want to get a histogram of the verb for that Apache log line. So the first thing that Elasticsearch would do is look up the host IP there in the index and pull a collection of documents that are for that host. It would then look in the field data for the verb, and we can see here there's gets and posts and puts. It would create buckets for the values there, get, post, and put, because those are the unique values within there. It then counts how many times that value, each of those values, appears in the field data for those fields. So this is the simple way that Elasticsearch does all of its aggregations. It first creates a document set that's a match for some query, whether it's match everything or whether it's filtered in some way. It then figures out all of the fields, all of the values that are in the field that you're interested in. It then computes some metric like count, or for numeric values, you can do min, max, average, standard deviation, all of that kind of mathematical calculation. So on the more complicated end, and one of the cool things you can do is you can actually sub-bucket. So I can say, okay, well, let's take the bucket of verbs and sub-bucket by the URL, for instance. So I can see how many gets are going against a particular URL. In this case, I'm looking at CloudTrail data here. I've bucketed by the ARN of the thing in the CloudTrail event, and then a region, and then an event name. And ultimately, I'm computing a count, and that's allowing me to generate a pie chart that shows me the breakdown within those different buckets. So this is less applicable for Elasticsearch 5. Elasticsearch 5, well, actually 5.1 within the service. Elasticsearch 5.1 has a different kind of field, which is called text field, which gets broken down into both the analyzed text and the keyword field. If you're using an earlier version, make sure you set the not analyzed flag for the fields that you want to use in visualizations. We talked about buckets and metrics and how that works. And then one of the ways that you dig into the data is to first put a date histogram on the x-axis. That splits everything into time buckets, and then you can build graphs on top of that. So we're going to wrap up here. Amazon Elasticsearch Service provides you an easy way to run Elasticsearch in the AWS cloud. Kinesis Firehose is a really great, robust way to get data into Amazon Elasticsearch service. And then you use Kibana for not only for monitoring, but also for analysis of the data underneath. I have a couple of links here. You can note them down now, or again, we will be sharing those links in the deck when we send it out. So I think we're going to move on to our Q&A. Let me see whether, Alan, are you back online?
I am back online.
Great. So Alan's going to lead us through the Q&A section.
Thank you, John, for taking over when I had my technical difficulties. So there's just a couple of unanswered questions right now in the queue. So the first one we'll tackle, it says, can we route our ELB logs through Firehose to automate the ingestion of them? And so the answer is today, no, you cannot write ELB logs directly to Firehose. ELB logs, of course, are in S3, so you could always write your own producer that takes data from the files in S3 and puts them through Kinesis. But currently, there's no integration between ELB logs and Firehose. The next question, does Firehose have dead mail delivery service? So you configure Kinesis Firehose to use S3 as your error destination. So for example, if you're writing to the Elasticsearch service and for some reason data cannot write successfully to Elasticsearch, Firehose will write that data to S3. Now if for some reason Firehose cannot reach S3, either the bucket is misconfigured or there's some kind of a networking issue, it will continue to write to S3 for 24 hours, at which time if it cannot persist that data to S3 in that 24-hour period, then that data will be lost. So it's imperative that you ensure that that S3 bucket is configured appropriately and available. Next question, is it possible to transform the data from Firehose into Parquet format before it gets to S3? Using the data transformation feature in Firehose, there's no restriction on what you do in that Lambda function for data transformation. So you can transform it to Parquet and return it to Firehose for persistence into S3. Bear with me as I look through the list of questions. Many are answered. So does Firehose maintain order on incoming data? So no, Firehose data is not guaranteed to be ordered. The producers that write data to Firehose, you do not provide a partition key, which with Kinesis streams, the partition key defines which shard a data record gets written into. And then inside of that shard, there is ordering guarantees. However, with Firehose, there is no partition key at the time of write. And so therefore there's no guarantee into which backend shard a given data record will be persisted. So there's no ordering guarantees with Firehose. And I believe that is all the unanswered questions.